and Power Cycling. Basically, you can have a software doing it for us, and we won't have to actually change the hardware or social engineer the user to do it for us. Of course, in this type of thinking, in using the BIOS platform, you can also have the big red button, which is a self-destruct one, which in any case, the BIOS can brick himself, and we have another effect on top of it. Questions? Cool. CD-ROM. How many people here knew that CD-ROM DVD drives have a firmware in it? That's not a whole lot of people. Basically, the region protection which the DVD and CD-ROM are using is a pure software, which meaning if you guys happen to see, when you buy a new computer, you have like this wizard that says, okay, you can use this DVD and read all the regions until like 5 times. And after the 5th time, whichever the region you chose is going to be locked. Of course, no hardware actually changed during this change. It's not like somebody comes and soldier a new chip into it. It's a simple software lock. So if you can use this to pick the region of your CD-ROM drive, you can also use this to pick not to read any region, which basically means you're going to break the drive. The drive won't be able to read any CD-ROM or DVD. And it's not because it's broken, simply the software in it will deny every CD-ROM. And of course, going back to my most straightforward example of overusing, a CD-ROM DVD drive has a very simple mechanical attack. Get the tray out, get it back in, do it as long as you want, and eventually it will stop working. So, a very simple Linux command, eject, and inject it, and try to get the tray back. Works like a magic, really simple and fun to execute. And again, doing it, imagine that you're hacking to a company. In the night, everybody goes back home, the company is shutting down, and for 8-9 hours during the night, all the computers are doing it at the same time. And I'm pretty sure that after a right amount of time, it will just wear them down one by one to the degree it will just not work, all the computers. When we spoke about the hard drives, I did mention solid-state hard drives. And the reason I mentioned it because flash memory as a concept has a vulnerability in it. And the vulnerability is basically the way the product is working. Flash really would like you to read information from it, would not so much like you to write information to it. And per design, there are programmable erase, PE cycles, which Flash can withstand before it no longer can be written to. Now, again, this is by design. It's applicable to all Flash products. And as you can see, there is quite a few of them in the market. We can go to distant keys, the most favorite external storage, and we can go to solid-state hard drives, which some computers are coming with built-in one, and thin clients, which are using this to boot from or using this as an entry point, and routers. Imagine that your company is buying some very expensive branded router, which of course operates on a flash, and a virus targeted this router and increasingly producing more and more write requests to the chip, to the flash. The conclusion will be in X time, the router will be useless. It will be disabled and it won't work anymore. This is a very, very straightforward example of how one can write random information to the flash. There are a couple of things you need to remember when you're taking a flash. There is an algorithm, a published algorithm about how the flash memory keeps trying to optimize blocks on it to avoid fragmentation. So this is not the optimized way of doing so. I don't think that for a proof of concept one should deliver it, but it's not very hard after you're reading the algorithm to design an application that will do it the quickest possible way. This method will work, but not will work as fast as if it were optimized. Network interface. Of course, NICs also can be flashed, and it's a very effective way to take down a very big product. For instance, one of the technologies that are pushing forward is the TCP offload engine, the TOE. The TOE is basically a statement that's saying to perform TCP/IP stack validations and functions on a general purpose CPU is a very difficult task. It's a very not efficient task. If you're supposed to deliver a 10 gig product that will do some DPI, for instance, you're an IPS vendor, an IDS vendor, a content inspection vendor, this becomes a very complicated task for you. So you would really like to offload some of it to your chip. Now, since we're talking about a TCP/IP stack, this is not a small piece of code. It's a huge piece of code, and there's many different bugs and patches. So the good guys at this alliance basically, per design, said that they will issue patches and, of course, security deliverables through firmware updates. And using this mechanism, you can basically, when you're attacking an appliance or when you're attacking an IHAND server, you can basically take off the network interface in a permanent way, thanks to this feature and to this design. So one of the assumptions that CSOs has told me is that, okay, you know what, maybe you're right, maybe you can do some damage, but you won't be able to do it to our old stuff, because back in the day, they made it like a good hardware. It's not this piece of shit today. So I was like, sorry to disappoint you, but I don't think it's true. And so I'm going to run through some legacy examples just to show that if you have something old, not necessarily means it's better or more bulletproof. It may contain the same logical defects as the new ones. And the CRT monitor is a very nice example of it. It's so simple to blow up a CRT monitor that the good guys at the X11 project, if you go and check out your X386 configuration file, you will actually see that they marked from themselves that when they run on legacy systems, these are the wrong ranges to use. Because if you will use this scale rate, there is a good chance the CRT won't withstand that and will just blow up. It won't have to blow up like in the movies, but it will blow up enough for not working anymore. So as you can see, you don't even have to write a sophisticated program. All you have to do is tweak some other program configuration, and the next time the user will click on it happily, it will do the damage for you. And this is the example of the CRT. Another example is a floppy drive. A floppy drive is sort of the last hardware equipment that you could actually see the software executes and how the hardware works. Hard drives today, thanks to cache mechanism and different algorithms, you cannot actually map one-to-one what is going to happen. But the floppy drive are very straightforward hardware. So one of the things that you can do here is basically excessively rotate the head of the floppy drive. And even I did a little research into it, because again, some of the knowledge here is not like cutting edge, it's already existed. So going back to the roots and see who exactly thought about it or had an idea about it, I actually found a virus called NIB, which did something very similar to it, but in the same way of walking from 0 to n, when n will be the last sector in the drive, and sometimes it will use n1 sector, so one that cross the thresholds, and the result will be the head is going to get stuck against the stopper, because the floppy will actually try to read something that's not physically accessible. I did read later that hardware manufacturers did implement validity check on it, but again, the very simple, straightforward attack works on a floppy drive. Okay, so again, some pieces from my conversation with CSOs. This time people were like, okay, you know what, you're right. Legacy is vulnerable, computers are vulnerable. Lucky for us, we have something handmade, crafted. You won't believe, some freaky architecture. It's not even Intel. Okay, it's not even Intel, doesn't actually mean there is no vulnerabilities in it. And this is another legacy example of a chip that was produced in the early 80s by Motorola. It was actually for a computer infrastructure. So eventually it was implemented in a mechanism, in a computer system. And it has a very interesting instruction called HCF, which they simply named for how to catch fire. It works similar to what I presented with the jump in the beginning for the Intel. Basically, it toggles each bus line so quickly that the system could not handle it, and as a result, there was an actual damage to the system. Now again, this chipset is no longer in use, and most likely that you will never encounter it, but it was again a proof of concept that it's not limited to personal equipment, it's not limited to everyday equipment. It can most likely happen in the most weirdest companies and the weirdest appliance you can ever come up with. Okay, so let's do a quick recap of what we just saw in terms of attacks. So we had the computer fans, again, not a target per se, but a way to get the system to get overheated. CPU, GPU, and RAM both can be overclocked and overvolted, and some of them could be bricked, depends on the hardware. Hard drives, both the solid-state ones and the traditional ones, can be attacked. Excessive writes, excessive reads, and in some cases, even bricking. The BIOS is a two-pipe sword for us. From one angle, it is a target. We can attack the BIOS and brick it. From the other angle, we can use it as a platform, use it to overvolt and overclock different elements in the infrastructure and damage them. External storage, like I said, the flash, this one here is an example, can be attacked. Network cards, CRT monitors, floppy disks, and non-Intel or non-x86 architectures. So I'm coming real quick to the end of my presentation. Again, most of the attacks that I show today does require local access to the hard drive. You either have to have an ability to run a code on it or the code on the system that the hard drive is included in it. But the flashing attack, going back to the original flashing attack, is actually a remote attack. So basically, if you look at how many devices nowadays, we have NAS appliances, we have Wi-Fi access points, we have DSL, ADSL modems, computers like peripherals like KVM, and even voice over IP phones. They all are really happy to receive updates, and not all the vendors are aware of the threats of this infection vector and attack vector, and as a result you can break the hardware really quick, really easily. One of the open questions